Chapter 8, Section 5, Solving Absolute Value Equations and Inequalities. Let's consider this statement. The absolute value of some number x is equal to 3. Now what we must remember is the definition for the absolute value of a number. The definition for the absolute value of a number is its distance from 0. So when you read this statement, it's really saying, find me all of the numbers whose distance from 0 is 3 units. Here's a picture. This is my x-axis, and what I really want is I want to find all of the numbers that are 3 units away from the origin or from 0. So if I count out 3 units, 1, 2, and 3, I find out that 3 has absolute value 3. But that's not the only number. If I go in the other direction, I find that negative 3 is also 3 units away from 0. So the absolute value of negative 3 is also 3. So we have two solutions. Either x is 3 or x is negative 3. These are the only two numbers whose absolute value is exactly 3 units. This leads us to a generalization that we can make that will help us solve other absolute value equations. So if the absolute value of capital X, which capital X represents just any algebraic expression, if the absolute value of this expression is equal to k, now remember k is going to have to be something positive because the absolute value is always something positive because of its definition. The absolute value of a number is its distance, and distance cannot be negative in this context. So k is guaranteed to be positive. So if you have an equation that looks like this, the absolute value of some expression is equal to k, then either that algebraic expression is equal to k or it's equal to the opposite of k. You did the same thing here. X was equal to 3 or x was equal to the opposite of 3. And that's the approach that we'll take when solving absolute value equations. Let's look at our first official example. We have the absolute value of x is equal to 3/8. All right, so this must be understood to mean find all the numbers x such that the absolute value of that number is 3/8 units. You can draw a picture again if you'd like. However, using our generalization up here, our rule, x will either be equal to 3/8 exactly, or x will equal the opposite of 3/8. These are our two solutions. Either x is 3/8 or x is negative 3/8. The absolute value of 3/8 is 3/8. The absolute value of negative 3/8 is 3/8. Let's continue. This says the absolute value of 6 minus 2x is equal to 12. All right, keep in mind 6 minus 2x, all of this in here is what capital X represented. Remember I said capital X represents any algebraic expression? Here is the expression, 6 minus 2x. So in order to solve this, we're going to split this into a compound equation. It's going to split into a compound equation. The first equation will read 6 minus 2x is equal to 12. Or 6 minus 2x is equal to the opposite of 12. Notice that I took the opposite of 12. That's what this says to do up here. Either your expression is equal to k or your expression is equal to the opposite of k. Notice that the only thing I changed in this second equation is the sign of k, the sign of 12, that is. I changed it to negative 12. I did not change the expression inside the absolute value bars. So don't change that. What you are changing is your constant. All right? And now all you have to do is solve each one of these equations separately, and then you have your two solutions. First thing I'll do over here is subtract 6 from both sides. Over here on the right, I'll solve this one simultaneously by subtracting 6 from both sides like this, and that leads me to negative 2x is equal to positive 6. And on this right side for this equation, I get negative 2x is equal to negative 18. What I'll do next for the equation on the left is divide both sides by negative 2. For this equation over here, I'll do the same thing, divide by negative 2. And then I have my two solutions. One of them is negative 3, and the other solution is positive 9. So these are the two numbers. Let's be really clear. These are the two numbers that satisfy this equation. What does that mean? Well, if you plug in negative 3 in for x, this expression on the left-hand side will be equivalent to 12. In other words, this whole left-hand side will be 12 units. Same thing goes for 9. If you plug 9 in, and feel free to do this, if you plug 9 in, this whole left-hand side will be 12. All right, cool. Let's look at another example. All right, the absolute value of x plus 1 over 2 is equal to negative 4. Wait a minute. We said earlier that the absolute value of an expression is defined to be its distance from the origin, or from 0. Distance cannot be negative. The absolute value, therefore, of any expression can never be negative, so then this equation has no solution. Okay, let's add something to your notes. Since the absolute value of an expression can never be negative, this equation has no solution. So we have to be very careful. If ever your absolute value equation is set equal to a negative number like this, then your answer is no solution. All right, let's move on. Check out this example. The absolute value of 3x over 2 plus 4, and then minus 3 is equal to negative 2. One might be tempted to say, oh, no solution because it's set equal to a number. But actually, what we must do first before we consider what this absolute value equation is really saying is add 3 to the right-hand side. In other words, and I'm going to write this down, before you do anything, the very first thing you should do when you have an absolute value equation is make sure that the absolute value expression is isolated. That is to say, make sure that the only thing you see on the left-hand side of the equation is the absolute value expression by itself. So then what we'll do first is add 3 to both sides of my equation, and then I'll consider what this is saying. So then I have this statement now. The absolute value of this expression is now equal to, watch this, positive 1. See, now this is saying the absolute value of something is positive 1. That's valid. So now we can solve this. How? Turning it into a compound equation with no absolute value bars. Do you remember how we do this? One equation is 3x plus 2. One equation is 3x over 2 plus 4 is equal to 1. The other one is 3x over 2 plus 4 is equal to negative 1. And then we solve each one of these separately, and then you'll have your two solutions. So let's do that. Now, the first thing I'll do on this left-hand side, and actually on the right-hand side as well, I'll subtract 4 from both sides. Okay. Some people like to get rid of the fraction right away. I don't. All right, 3x over 2 is equal to negative 3 over here on the left. On the right, I have 3x over 2 is equal to negative 5. Now, the next point I'm going to make is a very important one. Whenever I'm trying to isolate a variable, whenever I'm trying to solve for a variable, like in this case, x, and its coefficient, the coefficient on x is a fraction like 3 over 2. What I'll do is I'll multiply both sides of my equation by the reciprocal of 3 halves. The reciprocal of 3 halves is just 2/3. When you do that, it'll isolate your variable in one shot. So I try to show that here. So I'm multiplying both sides by the reciprocal of 3/2. The reciprocal is 2/3. Now the cool thing about it is the product of any number and its reciprocal is 1. So all of this turns out to be 1. After all, 2 times 3 is 6. 3 times 2 is 6. So this is really 6 over 6, which is just 1. In other words, x is now just 1x, all right? It's all isolated. X is by itself. And then this 3 and that 3 cancel, and you're left with just -2. There's one of your solutions. On the other side of this, let's see what's happening here. X is equal to, now there's nothing to cross cancel here because 3 and 5 have nothing in common. Let's not forget that -5 is really -5 over 1. So really all you're doing is multiplying straight across. So don't forget about that, guys. So then your final answer is just -10 over 3. That is your other solution. Okay? All right, next example. -2 times the absolute value of 1/3 x plus 5, then plus 6 is equal to 6. Now, be very careful here. What we never do is we never distribute inside absolute value bars like this, okay? So please do not distribute the -2. Another thing we cannot do is add 6 and -2 because they are not like terms. This -2 is being multiplied by this variable expression. All right, it's not like this -2 is a constant term standing alone that like the 6 is, and then you can add them and get something like 4. Can't do that, okay? All right, what we said earlier is very important to remember here. The very first thing we do is isolate the absolute value expression. This is the absolute value expression. In other words, this -2 has to get out of there somehow, and this plus 6 has to get out of there somehow. What I mean by that is we're going to have to do the opposite of adding 6 and the opposite of multiplying by -2. That's correct. This is multiplication by -2. This is not subtraction by 2. This is multiplication. This is read as -2 times the absolute value, okay? So the first thing I'm going to do is subtract 6 from both sides. Now, when you subtract 6 from both sides, you get -2 times the absolute value of 1/3 x plus 5 is equal to 0. Now, that's going to be interesting for us in this example. Then I'm going to divide both sides of my equation by -2. That's going to isolate my absolute value expression. And on the right, I still get 0 because 0 divided by any non-zero number is 0. All right, so what we do at this point is we turn this into a compound equation, right? We split it into two separate equations. 1/3 x plus 5 is equal to 0, and the other one is 1/3 x plus 5 is equal to the opposite of 0, which is still 0, right? The opposite of 0 is just itself. So you can see here that splitting this into a compound equation, having two separate equations, is redundant. For that reason, I will not solve the same equation twice. I'll just solve one, and we'll have one answer only. All right, so what I'm going to do then is subtract 5 from both sides. And that'll leave me with 1/3 x is equal to -5. Now remember what I suggested earlier. Whenever I'm solving for a variable and its coefficient is a fraction, I multiply both sides by the reciprocal. The reciprocal of 1/3 is 3. So I'm going to multiply both sides of this equation by 3. Like that. Okay. Now, if I can just move this up a little bit, give myself some more room. So the left-hand side is just x now, and the right-hand side is just -15, which is your one and only answer. All right, how about a little summary? All right, here's a summary for us. If k is a positive number, then this absolute value equation gives two solutions. Either x is k or x is negative k. So this is a compound equation. The first few examples were of this case. If k is negative, then the absolute value equation it doesn't have any solutions, right? It's no solution. Because if this number is negative, the absolute value of any expression cannot be negative. If k is 0, well, then this absolute value equation only has one solution, okay? So you set that equation equal to 0, and then you solve. All right, so either your absolute value equation has two solutions, one solution, or no solution. All right, everybody, this is the question I want you to consider. When are two absolute value expressions equivalent? When can we say the absolute value of one expression is equal to the absolute value of another expression? Well, to answer that question, consider the following. Would you say that the absolute value of this expression is equivalent to the absolute value of this one? What about this down here? Would you say the absolute value of this expression is equivalent to the absolute value of this expression? Of course you would. You would say that these both are equal because these two expressions, 3 and 3, are the same. Same thing down here, negative 3 and negative 3. The expressions within the absolute value bars are the same. All right, well, what about this over here? Would you say the absolute value of 3 is equivalent to the absolute value of negative 3? What if I told you the absolute value of negative 3 is equivalent to the absolute value of positive 3? Would you agree? Of course you would, because you know that both of these left and right hand sides are equal to 3 units. So these are true as well, and notice that the expressions within the absolute value bars are opposite each other. Same thing down here, negative 3 and positive 3 are opposites. So let's get back to our question. When are two absolute value expressions equivalent? The answer? Two absolute value expressions are equivalent if the expressions within the absolute value bars are either the same or they are opposite each other. Now remember, same or opposites, all right? They are either the same or opposites. All right, now let's go for this next example. Here we have two absolute value expressions that are equivalent. The absolute value of 4x plus 2 is equivalent to the absolute value of x minus 4. We just finished deriving that this equivalence is true only if this expression inside is equal or the same as this expression in here, or they are opposite each other. So watch what I do. This is true. This statement that's given to me is true if 4x plus 2 is equal to x minus 4, or 4x plus 2, watch this, is the opposite of x minus 4. All right? So this just turned into a compound equation. Notice the pattern. Everything's turning into a compound equation. And the previous lesson, 8.4, was all about compound inequalities. So it just seems like we're in this pattern of solving compound inequalities and compound equations. All right, what we should do is solve each one of these equations separately. Now, just a small word about this right-hand side. I chose to keep the left-hand expression the same and take the opposite of the right. You didn't have to do that. We could take the opposite of the left expression and keep the right expression the same. Up to you. Okay, on the left-hand side, what I'll do is subtract x from both sides to attempt to get my variables on the same side. On the right-hand side, I'm going to go ahead and get rid of these parentheses by distributing that negative. On the left, that leads me to having 3x plus 2 is equal to negative 4. On the right, I'm getting 4x plus 2 is equal to negative x plus 4. On the left-hand side, what I'll do next is subtract 2 from both sides. Over here on the right, I'll add x to both sides to collect my variable terms on the same side. The left-hand equation turns out to be 3x is equal to negative 6. On the right, I have 5x plus 2 is equal to 4. On the left-hand side, I'll wrap this up by dividing both sides by 3. On the right-hand side, I'll subtract 2 from both sides. On the left, I have one of my solutions, which is x is equal to negative 2. On the right, I have 5x is equal to positive 2. On the right, I'll divide both sides by 5 to wrap this up. And I have my second solution, which is x is 2/5. So this absolute value equation that has two absolute value bars has two solutions, negative 2 or 2/5. All right, we've solved absolute value equations that have one set of absolute values, and then we've also solved an equation that had two sets of absolute values. Now, we will shift our attention for the rest of this lesson to absolute value inequalities. To get us started, please consider the next statement. The absolute value of some number is less than 3. Now, by definition, that means find all of the numbers that are less than 3 units away from the origin. All right. Allow me to draw a picture to help us understand this statement. All of the numbers whose absolute value, whose distance from 0 is less than 3 units, are these numbers here. I'll put a parenthesis on 3 because this is a strict inequality. So these are the numbers here that are less than 3 units away from the origin. But that's not it. These numbers here also have absolute value less than 3. These numbers here are also less than 3 units away from the origin. So really, what ended up being your solution? Well, this part here says x is less than 3, right? This part here, this half is x is less than 3. And this part here, from 0 to negative 3, says x is greater than negative 3. X is greater than negative 3. That's what that says. This part says x is greater than negative 3. Now, in order for you to make it into the final solution set, right? This is the final solution set for this inequality, ladies and gentlemen. All of these numbers here, all of them have something in common. All of these numbers are both less than 3, and at the same time, they're greater than negative 3. For example, let's take the number 2. 2 is less than 3. Yes, it is. 2 is also greater than negative 3. See how it satisfies both of these? Let's take another number, negative 1. Negative 1 is less than 3. True, satisfies that. Negative 1 is greater than negative 3. Yes, it satisfies this. Every single number in this solution set satisfies this inequality and this inequality. What we just figured out right now is that this absolute value inequality has the word and adjoining or joining these two inequalities, right? The word and should be the word there, is the correct conjunction. Why is that so important? Well, in the previous lesson, we learned that a compound inequality joined together by the word and implies intersection. So what we just figured out is that absolute value inequalities with the less than symbol means it's an intersection problem. So we're going to turn every absolute value inequality with the less than symbol, we're going to turn it into a compound inequality with the word and in the middle, which implies intersection. All right, let's apply what we just learned. So whenever you have the absolute value is less than some number, like we have here, turn it into a compound inequality with the word and in the middle. All right, here we go. You ready? Watch this. This absolute value inequality turned into this compound inequality. Watch this. This first inequality looks exactly the same as this one. So the first inequality that I have for this absolute value inequality is this one. 3x minus 1 is less than 8. It looks exactly the same. The other one that I'm going to get, however, notice here, what changed between this inequality and the original? What's different? Two things. The inequality symbol used to be less than, and now it's greater than, so the symbol changed. And then, instead of positive 3, you have negative 3. So that means for this inequality here, I'm going to have 3x minus 1 is now greater than negative 8. See those two changes? And then the word that's right in the middle is and, implying intersection. This is going to be an intersection problem. Okay? Keep that in mind. All right, here we go, guys. Please notice this pattern, okay? We're going to solve each one of these inequalities separately, all right? On the left-hand side, I'm going to add 1. Okay? On the right-hand side, I'm also adding 1. So that leads me to 3x is less than 9, or 3x is greater than negative 7. What I'll do next is divide by 3. And so I have my final statements, which are x is less than 3 and x is greater than negative 7/3. All right, everybody. Keep these in mind here, all right? The word that's in the middle is and. So in order to make it into the final solution set, you're going to have to satisfy both of these statements. Let's draw a picture so that we understand what is going on in this problem and what all of this means. Here we go. Here's our x-axis. Okay? Here's 0. 1, 2, 3, right there. Negative 7/3. Notice that 3 goes into 7 twice with 1 left over. So this is the same thing as negative 2 1/3. Okay, or negative 2.33333333. Basically, this value here is going to be found between negative 2 and negative 3. So negative 1, negative 2, negative 3. Okay, so here we go. Do you remember that the word is and in the middle? Here, I'll make it really explicit that the word in the middle is and. I'll actually write it for us, okay? So and, okay, intersection. So in order for you to make it into the final solution set, you have to be a number that is less than 3 and greater than negative 7/3. I'll say that again. In order to make it into the final solution set, you have to be a number that is both less than 3 and greater than negative 7/3. So you have to be less than 3 but greater than negative 7/3. So this is your final solution set. These are all of the numbers that are greater than negative 7/3, but they're also less than 3. Interval notation, read your graph left to right. You got a parenthesis at negative 7/3 all the way to a parenthesis at 3. This is interval notation. Man, that was fun, wasn't it? Let's do another one. I like this example, number 8. It says the absolute value of negative 5x plus 4 is less than negative 10. Let's think about this really quickly, folks. Isn't the left-hand side an absolute value expression? Yes, it is. So then, isn't the left-hand side something positive? Because isn't the absolute value of any expression positive? Yes. So this left-hand side, the left-hand side is positive. What about the right-hand side? Well, that's a negative 10, so it's negative. So I have a question for you. When will something positive be less than something that is negative? When will this relationship ever happen? Never. This is impossible. Something positive can never be less than something negative. So your final answer here is no solution. So we know how to solve an absolute value inequality with less than, or even less than or equal to. The same is true. But here, now we have an absolute value inequality with the greater than symbol. So let's really consider what this is saying. By definition, this is asking for all of the numbers whose distance from 0 is more than 3 units. Sometimes pictures help us understand. So I'm a fan of drawing you guys these pictures. So, all of the numbers whose distance from 0 is more than 3 units looks like this. Those numbers have absolute value greater than 3. These numbers also have absolute value greater than 3. So then this here says all of the numbers that are less than negative 3. This one over here says all of the numbers that are greater than 3. Now, you don't have to satisfy both of these. Actually, it's impossible to satisfy both. It's impossible to be a number in this set and in this one, right? You can't be greater than 3 and less than negative 3 at the same time. But you can satisfy either one. In other words, the word that should be in the middle here, joining these two inequalities, is the word or. You got it. An absolute value inequality with the greater than symbol represents a union problem, not intersection. All right, notice that it turned into a compound inequality again. This inequality looks exactly the same as the original, and this one, you can see it, can't you? The inequality switched, just like before, and instead of positive 3, you have negative 3. Let's use that pattern. All right, let's see if we can use that pattern on this example. You got the absolute value of 5x minus x divided by 2 is greater than or equal to 3. Now, I know that's strict and this is non-strict, but the same pattern holds. All right, so what we're going to do is we're going to split this into a compound inequality. The first one will look exactly the same. The other one, two things will change. The symbol will now be less than or equal to, and then instead of 3, you got negative 3. Now, the word right in the middle is or, which is implying union. You want to find the union of these two sets. All right, so we've done this often now. Let's solve each one of these inequalities separately. All right, on the left-hand side here, I'm going to multiply both sides by 2. That will clear the fraction, okay? So I'm going to multiply this side by 2, multiply that side by 2. That will get this 2 and that 2 to cancel, and I'm just left with 5 minus x greater than or equal to 6. On the left-hand side, I'll do the same thing, all right? So I'm going to multiply the left-hand side by 2, and I'll multiply the right-hand side by 2 as well. That'll get my fraction to go away, and I'm left with 5 minus x is less than or equal to negative 6. On the left side here, I am going to subtract 5 from both sides. Same thing over here, subtract 5. And what that gives me is negative x greater than or equal to 1. Over here, negative x less than or equal to negative 11. Now, I'll divide both sides by negative 1 on both of these sides, right? Now remember what happens when you divide by a negative? Switch the inequality symbol. Less than or equal to negative 1 is one statement. And the other one is x is greater than or equal to 11. All right. Do you remember what's right in the middle of these two sets? Yep, the union, right? So let's graph each of these and find the union of these two sets. All right. So here's my number line. Here's my x-axis, okay? Now, if you don't mind, I am going to just say this is negative 1 on the x-axis, and I'm going to say this is 11 on the x-axis. All the numbers that are less than or equal to negative 1, less than or equal to negative 1 look like that. All the numbers that are greater than or equal to positive 11 look like this. This is the final solution set, okay? In interval notation, you'll read your graph left to right. This is an arrow pointing to negative infinity, so it's negative infinity all the way to negative 1 bracket, union, and then pick back up at 11 and then go to the right forever, all the way to positive infinity. So here's the final solution set, the graph of the solution set, and the solution set written in interval notation. Okay? Check out this example. Example 10. 7 is less than or equal to the absolute value of 3/5 x minus 1 and then plus 2. Now, I don't know if you remember from an earlier lesson, a much earlier lesson, I strongly recommended that we keep the variable on the left side of the inequality symbol at all times. So what I'm going to recommend is that we just turn this whole inequality around. Instead of saying the left-hand side is less than or equal to the right-hand side, that's the same thing as saying the right-hand side is greater than or equal to the left-hand side. Okay? So I can rewrite this as the absolute value of 3/5 x minus 1 plus 2 is greater than or equal to 7. So I basically read this from right to left, which is a little awkward. But I like this better because the variable is now on the left. Now what I'm going to do is I'm going to isolate the absolute value expression. Remember, that's always what we do first. Isolate the absolute value expression. And we get the absolute value of 3/5 x minus 1 is greater than or equal to positive 5. Now, what kind of symbol do we have? Don't look at the original because that wasn't written in the right form. Now we have it. It's greater than or equal to, just like the previous problem. So is this intersection or union? Union, because it's greater than or equal to. All right, so what we're going to do is we're going to turn this into a compound inequality, right? The first inequality will look exactly the same as the original, as this one, not the original, but this one right here, right? Greater than or equal to 5. Now the next one will be 3/5 x minus 1 is less than or equal to negative 5. Remember, those two things change, the symbol and the sign. Now, don't forget, we're finding the union of these two sets, all right? All right, here we go. On the left-hand side, what I'll do is add 1 to both sides. Same thing over here. That'll lead me to 3/5 x is greater than or equal to 6. Over here, 3/5 x is less than or equal to negative 4. What I'll do next on this left and right hand side is I'll multiply both sides by the reciprocal of 3/5. The reciprocal of 3/5 is 5/3. So I'm going to multiply this side by 5/3, right? Alrighty, by 5/3. All right. So let me just, all right, here we go. So 3/5 x is being, so both sides is being, of this inequality are being multiplied by 5/3. Same thing over here for this inequality on the right. So 5/3. And then if I can fit it here, barely 5/3. All right. So I got this inequality. Thank you for being patient. All right, there we go. Multiplying both sides by 5/3. Now remember that the product of any number and its reciprocal is just 1. So this is just 1x here. So just x is greater than or equal to. And then I always cross cancel if I can. 3 goes into 6 twice. So you get x is greater than or equal to 2 times 5, which is 10. All right. So then this one is done. Let's go over here to the right. I get x is less than or equal to, and there's no cross-canceling happening here. Also, don't forget that negative 4, if you want, is really over 1. So when you multiply straight across, you get that x is less than or equal to negative 20/3. All right, so that one is done as well. All right. Remember what we're taking between these two sets. Their union, all right? So let's go to the graph here. Let's go to the x-axis. Here's my x-axis. All right, and if you don't mind, I'm going to say this is, I'm going to say that this is 10 here. And I'm going to say this is negative 20 thirds here. Negative 20 thirds, 3 goes into 20 6 times with 2 left over. So this is the same thing as negative 6 and 2 thirds. So this number, negative 20 thirds, can be found between negative 6 and negative 7, a little closer to negative 7 than to negative 6. All right, so here we go. We are going to show all of the numbers that are greater than or equal to 10. All the numbers greater than or equal to 10 are in that direction. All the numbers that are less than or equal to negative 20 thirds, less than or equal to negative 20 thirds are in that direction. So there's the final, the graph of the solution set. And when I write the solution set in interval notation, I go left to right, so negative infinity to negative 20 thirds, bracket, union, bracket at 10, all the way to positive infinity. Cool, you guys. Let's do one last one. This one's interesting. The absolute value of this expression is greater than negative 8.6. Now, before we do a lot of work here, let's really consider what's going on. We already know that the absolute value of any expression can never be negative. Said another way, the absolute value of any expression is always positive. So I hope you agree with me that this left-hand side has to be positive. The right-hand side is negative. It's a negative number, negative 8.6. Now here comes my question. When will something positive be more than something negative? All the time. That's right. This relationship is always true. So then your final answer is all real numbers. No matter what real number you plug in, the absolute value of this expression will always be more than this negative value, no matter what you plug in. Okay, so all real numbers is our final answer. You know how to graph all real numbers, right? Here's your x-axis, and you just show a line going in both directions like that. So here's the graph of all real numbers. Here's all real numbers written in interval notation, okay? How about a little summary before we end? All right, guys, let's walk through this little summary together. These are, in yellow, absolute value inequalities with less than or equal to. They're both intersection kind of problems. That's the symbol for intersection. You're going to turn it into a compound inequality with the word and in the middle. Notice that the first inequality is always the same as the original, right? Nothing changed. The second inequality, two things changed, the symbol and the sign on your constant. Same thing here. This is non-strict. It's a compound inequality with the word and. First inequality is the same. The second, two things change, the symbol and negative k. These ones in red are greater than or equal to. These are union type of problems. But the same pattern, folks. Same exact pattern. It turns into a compound inequality, this time with the word or in the middle. But the first inequality is exactly the same. The second one, notice the two things that change, the symbol and the sign. Greater than or equal to, it's a compound inequality with the word or. First inequality looks the same. Second one, the symbol changes and the sign. Please, if you can learn math by following the pattern, I think that would make a lot more sense and help your learning. So how do you know when you're solving an absolute value inequality, whether you're looking at an intersection kind of problem or a union? Well, it depends on the sign. It depends on the symbol. If it's less than or equal to, that is a that is a intersection problem. If it's greater than or equal to, it's a union kind of problem. A student of mine once shared this to help them remember between intersection and union for these kind of problems. They said, think of it in terms of money, professor. I said, okay. And they said, um, less money will make me sad. Whereas more money will make me happy. All right? So less money, that's less than, will make me sad. This is intersection. More money, greater than, is more money, will make me happy. Now, okay, I am not advocating for our happiness to be dependent upon money, okay, by no means. But in the context of absolute value inequalities, this kind of works. So keep in mind this little trick or whatever is also true for less than or equal to, and then this one is also true for greater than or equal to. I don't know if that helps you. If it doesn't, then just pretend I never said that. But I do share that occasionally, and I give credit to that student that showed me that. So anyway, not sure if that was helpful. I hope you learned in this section, and I'll catch you in the next section, which will be the next lesson. The next lesson will be 8.6, and we're going to be talking about factoring. We're going to review how to factor polynomials, all right? So this is the end of this lesson. I'll catch you later.